Are you ready?
Yep.
All right. Uh, so let's get started. So our next talk is by Jiseong Jiseong Kim from University of Mississippi, who will be talking on shifted sums of multiplicative functions.
Okay. I would like to thank the organizer for giving me this opportunity. And today we will talk about the shifted sums of multiplicative functions. So let me talk about the shifted convolution problem first. So let f and g be arithmetic functions. Then a shifted convolution problem for f and g, consider this summation, sum of fn times gn plus h, when h is an integer. So the goal of this problem is to find asymptotic formula or upper bound of this summation. And this problem is quite relevant to other topics. So when f and g are free coefficients of orthogonal forms or just divisor function, then this is relevant to the subconvexity and moment problems of the corresponding L functions. And when f and g are the von Mangoldt function, then this is just the Hardy-Littrude K-tuple, prime K-tuple conjecture. And if you put x minus n here, then it is the Goldbach conjecture. So if you want to consider in some vector setting with more than two multiplicative functions, then there are also many research on this kind of summation. And first, Hermitiusson proved the asymptotics when h sub I are divisor bounded and its mean values over arithmetic progressions are stable. And the function pi sub I are linear polynomials, but they are pairwise independent. And in another direction, and Franzkinakis and Host proved the asymptotic of this one when h sub I are bounded pretentious multiplicative functions, and these pi sub I are linear polynomial. We say that the function h sub in is pretentious when it is behaved like some Dirichlet character times n to the power of I sub t, it. And Kuhlmann improved their result for the case when h sub I are bounded pretentious and pi sub I are any integer polynomials. So now let me talk about the additive divisor problem. So we define the case order divisor function as a standard way. So this sub kn is just the number of ways to represent n as the product of k integers, natural numbers. And there are various research on this topic, but one of the famous theorem is from de Chaulier and Ioannis. And they proved that the shifted sum of d sub 2n times d sub 2n plus h is some polynomial of degree 3 log x times capital X with this power saving error term. And then there are many research on the average version too, but one of the most recent work is from the Matomaki, Rajul, and Tao. And they proved that when k and l is fixed greater than or equals to 2, and when h is greater than x to 8 over 33, then they shows that for almost all shift less than capital H, they proved the asymptotics of the shifted sum d sub kn times d sub l n plus h. And this polynomial is actually easily calculatable. There are many heuristics, and they actually give us the precise value of this polynomial. And you can see that there's a arbitrary log power saving. So they use the fact that d sub kn can be represented as a Dirichlet convolutions of the indicator function. And because the indicator function is just, it has a very good cancellation property, which is somewhat like it is stable on the arithmetic progression. And also we can apply various mean value theorem and exponential sum estimate. So they use the fact that this indicator function has a good cancellation property. And let me talk about our previous work. So we applied their method to prove the asymptotics of the square of the Hecke eigenvalues. So let's denote lambda n as the nth normalized Fourier coefficient of holomorphic Hecke custom. Then we proved that when the capital H is greater than x to 2/3, the shifted sum of lambda n squared times lambda n plus h squared is equals to some constant times capital X with the log power saving error term for almost all shift h less than capital H. So as they applied the Dirichlet convolutions of d sub kn, we applied the Hecke relations, which is lambda n squared can be represented as the indicator functions as a Dirichlet convolutions of the indicator function and lambda m squared. And it is well known that this lambda m squared is actually the m's normalized Fourier coefficient of the GR3 automorphic form. But compared to their work, we don't know much about the information about this lambda n squared. So we don't know that lambda n squared has the good cancellation property. So instead of using this cancellation property, we applied the Miller's very nice bound on the exponential sum of lambda n squared e alpha n, which is bounded by x to the 3/4 plus epsilon. This result is very nice. And you can see that this is this is satisfied uniformly. It doesn't rely on alpha. And then to extend the range of h, we apply some Gallagher's lemma. So my question is, I wanna get some this kind of result for more general multiplicative functions. And I also wonder how to save the power saving instead of the log power saving. So before we talk about the main theorem, let me state the assumptions. So we define f sub k as the class of multiplicative functions g, which satisfies the following properties. So the first one is actually just the divisor bounded. We just assume that the gn is bounded by some divisor function. And actually, if you assume the Lagrangian conjecture, then you can also get this one too. And we also assume that the F function of g twisted by the Dirichlet character satisfies some very nice analytic properties. And we also assume that this F function doesn't have any pole. But it is just for simplicity. I mean, it is okay to have pole, but the argument will be a little bit more complicated, but it is still doable. And we also assume that the square moment, the integral of the square of the L function is bounded by q to the epsilon square times t plus 1 to the power of 1 plus epsilon square. So if you assume the generalized Lindelof hypothesis, then you can get this result directly. But I want to say that this condition is much more weaker than the generalized Lindelof hypothesis. And now we define S sub k, which is the set of function that can be represented as the Dirichlet convolution of g and the indicator function for some g in f sub k. And now let me state the main theorem. So we proved that when f is in S sub k and h is greater than x to the 87 over 88, then we can actually get the asymptotic sum with main term b sub hx with the power saving error term for almost all shift h. So the nice thing for this theorem is we have the power saving. So first we start with the hotly through the circle method. So let S alpha is the exponential sum of fn times en alpha, and we use this standard notation. Then we can represent the shifted sum as the integral of S alpha squared times E minus H alpha. And then as a usual way, we separate this integral as the major arc part and the minor arc part. And major arcs are the alpha, which is near to A over Q. Q is smaller than capital Q. And minor arc is just the remainder part after the major arc. And we set capital Q as x to the 1 over 22. And we set major arc as the union of intervals of length x to the minus 10 over 11. And minor arc is just the complement of the major arc. So for the proof of the main theorem, we proved these two propositions. The first proposition is about the major arc. So we showed that the major arc estimates give us the main term b sub hx plus this these power saving error terms for almost all shift h less than capital H. And minor arc part is a little bit different. And this one is we consider the integral of S alpha square over the very short interval on the minor arc. And we have the power saving in here. So let me talk about the proof of the main theorem, assuming these propositions. So let x sub h is the actual minor arc estimate. So because we just want to show that x sub h is small for almost all h, so we can apply the Chebyshev inequality. So the probability of the xh, which is greater than x to the beta, is just bounded by the average value of xh squared over x to the 2 beta. So now we just need to show that this averaged version of the minor arc is smaller than h times x to the 2 beta. And after smoothing over h, we can bound this term as this form. So we have h here, and now we have this term, and this is the one that we consider in the propositions for the minor arc. So we apply this one to this, and then we just use some trivial bound of on the unit interval, and then we just multiply h. So we can actually prove these types of upper bound. And let me talk about the major arc estimates, and it is quite standard. So first we consider the sum of fn with additive twist a over qn. And by the standard method, we can change this a over qn as some linear combinations of the Dirichlet character. So now we have some linear combinations of the multiplic f times chi of n. So which means that we can apply various analytic properties of the f functions twisted by Dirichlet character. And then apply, because we skip the e beta n, so to attach e beta n, we just apply the integral by part. So the original exponential sum is now can be represented as the sum of constant times the integral of e beta x dx, which is much simpler than the original form. So because this integral is much more simpler, so by the pre-inversion formula, we can actually calculate this as x plus small error term. So major arc estimate is now just a linear combinations of the integral of the square of integral x to 2x e beta x dx. So now it just gives us some main term b sub hx with the small error term. So major arc estimate is quite simple. but minor part is a little bit complicated, but it is doable. So let me talk about it. So we will use the fact that f is the Dirichlet convolution of g and the indicator function. So we can represent the exponential sum as some double sum of g and the exponential sum. And we separate this integral into two parts. So the first part is d is greater than y. So this exponential sum is on the short interval in some sense. But this one, we restrict the size of d less than capital Y. So this exponential sum is relevantly long, So we can apply various exponential sum estimate and moments estimate for the Dirichlet function. But this one, we cannot apply it because the length of this exponential sum is too short. So we need to treat this in a different way. So the first integral, we apply this upper bound for the exponential sum. And this one just comes from the Mellin inversion formula and the method of the space method of steepest and descent. So this one is now can be, just rearranging the original one, we can represent this as this form. And we have the upper bound of this summation. So we just apply this pointwise upper bound for the first integral. So we can actually get we can actually get a small upper bound in some sense. And for the second integral, we transforming the exponential sum as in terms of the Dirichlet polynomial. So for this one, we smoothing over gamma. So we can and applying the French-Harris theorem, we can give the bound for this one as this one. And then by apply the literal parity decomposition and method of stationary pace, we can consider this one as some linear combinations of the integral of the Dirichlet polynomial. So now we have Dirichlet polynomial, so we can apply various mean value theorem. So for that part, we consider two types of the case. The first case is type D1 sum, so which is the support of G is very short, with just less than x to the epsilon square, but indicator function is supported on very long interval. So this one is actually behaves very similar to the indicator function. And so the type 2 sum is this G has a quite long support, but it is still short in some sense. So the integrand of the second integral is now transformed as this double sum with Dirichlet polynomials. And these Dirichlet polynomials can be, this is just can be represented as a linear combinations of type D1 sum and type D2 sum, type 2 sum. So we apply the propositions of Matsumaki and Ajiri, and they prove the exact upper bound of this one. So you can see that the original integration is now bounded by some linear combinations of the integral of the moment of the Dirichlet polynomial. So type D1 sum is treated by our first moment theorems for the Dirichlet function because the support of this one is sufficiently long. And for the type 2 sum, we just apply the standard R-square moment theorem. Okay, let me finish it here. And thank you very much.
Are there any questions for our speaker? Oh. Let's thank Jiseong again.